Okay, so this is our only meeting for the week, right? We have officially 3 days left of lecture. Last time, the main result that we had was that if we had the expression 1 over 1 minus, I'll say u instead of x, that this could be written as the power series. Anyone remember? N equals 0 to infinity of u to the n. As long as the absolute value of u was less than 1, correct? So as long as the absolute value of this thing in here is less than 1, then we can always rewrite this expression in this format. And then from that, I did some examples showing you that if we had something that didn't look exactly like that, but kind of like it, we could tweak it. We could kind of make it work out, right? One example that we did, or I'll do an example just to get our brains going. I know you've been focusing on other things probably. Let's say we have, I'll just make it up. We have something like 1 over 1 plus 5x, that we could write that in a power series by recognizing that this is the same as 1 over 1 minus negative 5x. And then in that case, our u, right? Our u is the negative 5x, right? The u that we have here is this. And so I can go straight to the summation n equals 0 to infinity of u, which is negative 5x, to the n. And that's what it'll be, right? So long as what? The absolute value of negative 5x is less than 1, which is the same as saying 5 times the absolute value of x is less than 1, which is the same as saying the absolute value of x is less than 1/5, right? So as long as the number that you plug in here, its absolute value is less than 1/5, then this expression turns into this power series. Yes? And then we could, if we wanted to, rewrite this as negative 5 to the n x to the n. And that we usually do this because the general definition of a power series looks like this. It's summation n equals 0 to infinity of c sub n x to the n. That's what a power series looks like. Right? When I first said what's a power series, this is what I put up on the board. I said it's some constant that's controlled by n times x to the power n. So if I write it, see up here with the negative 5x to the n, we don't have the x by itself, right? So I try and get the x by itself, so I rewrite it this way. And then this negative 5 to the n becomes my constant term. Now, I mean, it's a constant for each term of the series. It still depends on n to figure out what the number is, but the c is a function of n. Yes? Good? Okay, so that's what we did last time. So now I'm going to give you some new stuff, some other things we can do with power series, and then we're going to continue to try and find more representations of power series. So our big first note for today is what's called term by term differentiation and integration of power series. So if you recall, when we learned derivatives in Cal 1, we were taught that if you had something plus something or minuses between, right? If you had separate terms, and if you took the derivative, you just did each term separately. And integrating was the same way. If you had integrating multiple terms, you could do integration on each term. So we call that term-by-term differentiation or term-by-term integration. Well, all of that extends over to power series. Since power series are just a bunch of terms, then we should be able to differentiate them term by term and integrate them term by term, which is the case. All right, so let's take a look at, well, we can differentiate and integrate as long as the power series converges. If it diverges, then it doesn't make sense to do it. So let me give you a theorem, and then we're going to see there's some formulas, and we'll apply those, all right? So here's the theorem. The theorem says if a power series and I'll write out what the power series is, sum n equals 0 to infinity of c sub n and then x minus a to the n. Now, this is the power series. How do we say this? It's been shifted, right? So we call this the power series about A, right? We talked about this when we first introduced power series. If the A is not here, then we say that the A is 0. So a lot of the power series we've dealt with up to now, we have not shifted. They've all been, about 0 or letting A be 0. But that's the more general formula for a power series right there. So if a power series has a radius of convergence of R, which is greater than 0, then the following things are true. Now, let me explain what this is saying. This would have been a good quiz for today, right? If you're given a power series, when in terms of convergence, what are the three possibilities with convergence? It's either going to do what, or what? Remember? Converge only when x is equal to a. That's the first possibility, because if x is a, that's 0, and it's a bunch of terms of 0, and that adds up to be nothing, so it would converge. So it either converges only when x is a, or it converges everywhere, or it converges on an interval, right? Those are the three possibilities for a power series. So this is saying that, let's say you have a power series, and it converges on its interval of convergence, or its radius of convergence, is bigger than 0. That's basically saying it could be two of those three cases, right? If x is a, then it only converges at one point. So then the radius of convergence would not be greater than 0. So this is saying if it converges everywhere, or if it converges on an interval, if that's our assumption, all right, then here's what we can say. Understand? Okay, here's what we can say. First of all, we can rewrite the original power series as a function I'm not changing anything. I'm actually defining a function f to be equal to that power series. And let's just write out what f looks like. If I start plugging in values of n. So if you plug in n is 0, you get what? C sub 0, right? X minus a to the 0 is 1, isn't it? So that would just be c sub 0. Then we have, let n be 1, c sub 1, then x minus a to the first power. Then plus c sub 2, x minus a squared, plus c sub 3, x minus a to the third, and so on and so forth, right? That's what the original power series is, right? So what I'm interested now is what would the derivative of that be? What would f prime be? So I'm writing that down. We have that. So I'm saying if this power series has a radius convergence greater than r, then the power series can be written this way. And The derivative of that power series would be what? So let's just try it. Let's just do term by term differentiation on this right here. What's the derivative of C naught? 0. So I'm going to write that down. What's the derivative of, so I say plus, what's the derivative of C1 times x minus a to the first power? So C1's a constant, right? I'm differentiating with respect to x. So x is my variable, right? So this derivative of right here is just 1. So this is just C1. Just C1. Plus, now my C2 again is a constant, don't worry about it, but here I have my linear expression to the second power, so I need to do like a chain rule. 2 comes out, right? 2 times C2. And then I take the power down 1 time, right? The power is going to come down, so it's x minus a to the first power, then times the derivative of what's inside, which is just 1. Yes? Then the next one would be what? 3 comes down, C3 this time, right? X minus a this time, power comes down to squared, then times the derivative of what's inside, which is 1. And then I keep doing this, right? Without even needing it, I'll just write down what the next one would be. It'd be what? 4, C4, x minus a to the third. Now, I'd like for us to write this new power series, right? This is a new power series. I'd like us to write that in sigma notation. So this would be the sum, right? Sum you tell me. You want to what? You want to start n at 1, why not 0? I mean, you're right, but why not 0? Look, this is gone, right? So if I did this, if I wanted to get C1 to be my first one, I call this Cn, I would need to start n at 1, wouldn't I? That would make this one appear. And then, what is this number right here? That's going to be, that's just n, right? So maybe if I put this right here, n, hold on. N right there, that's n, right? That's my, if I plug in 1, I'd get a 1 C1. Then the next time I'd get what? A 2 C2, then a 3 C3, then a 4 C4, right? So that should, I need to squeeze that in there. I need a little more room. N times Cn should take care of the constants, right? And then what about the powers? What about these x minus a's? Well, I don't have one here, and then it's to the first power, then the second, and the third. So the power on the x minus a is always 1 less than the n, right? So n minus 1. So this is x minus a to the n minus 1. Do you all agree with that? Well, wait a minute. Hold on a second. If you just go back up here, and I say, what's the derivative of this, right? This is a constant. This is x to a power, right? You apply the power rule, right? The n comes out, right? N. Then all of this, you reduce the power by 1, n minus 1. That's this, right? The n came out. We reduce the power by 1. But what's the one adjustment we had to make? Where we started. That's the thing you have to remember about the derivative, the power series of the derivative. Sorry, the derivative of a power series. You have to shift the index over by 1. If you accidentally start this at 0, right? Well, what would happen? You'd get 0. That would be okay. Yeah, it'd be okay. It'd be okay here, but there are cases where it would cause a problem, and you would get a first term that would mess up, because we could have more than just this. We could have another power series over next to it. So just trust me on this for now. I'll show you some examples. We just shift the index over by 1. All right? Just remember that. Other than that, it's just power rule. N comes down, subtract n. All right, now also we stop at infinity. Well, we don't stop, I should say. All right, so that's pretty straightforward. All right, what about integration? So what would the antiderivative of f of x, of course, with respect to x be? So let's do it term by term. What's the antiderivative? This is our f, right? What's the antiderivative of c naught? C naught x. What's the antiderivative of c1 x minus a to the first power? 1/2 c1 x minus a squared. So this is going to start to take on the same sort of format as the power rule for antiderivatives here. What's the antiderivative here? 1/3 c2 x minus a to the third, and so on and so forth. Now, of course, at the very end of this, we would have a constant, wouldn't we? But we can't have an end to it, can we? We can't have an end to it. So what we do is we usually throw in front over here, right in here, we throw a plus capital C. We know that when we take an antiderivative, we're going to be off by a constant. Okay? So this plus C. So what would our formula be then? Can we come up with a general formula for this? Power series. N equals, I can start it at 0 this time, because that's going to give me my C sub n. So if I plug in 0, I get C0 to start. But what about that number in front? This is, what's the number, not the C, but what's the number here, the number here, number here? 1 over n, 1 over n, 1 over, not n though, 1 over n plus 1. Remember the antiderivative is always n plus 1. If I start at 0, then the antiderivative, right? What's the antiderivative of x squared? 1/3 x cubed, right? It's always 1 over n plus 1, x to the n plus 1. So this is going to be 1 over n plus 1. Then we have our constant. Then over here, we're going to have x minus a to the, what? N plus 1 again. And then, of course, we have like a plus c, all right, out there. And we can separate that. This is an infinite series, and then we're adding some constant out here. Make sense? So if you're looking at something like a power series here, you want to know the antiderivative, you just, whatever that power is, bring it out, 1 over n plus 1, and then you add 1 to that power. That's the antiderivative. If you want to know what the derivative of this is, you bring the n out, you subtract 1 from the end, and you shift the index 1. And that's your derivative. Got it? So we don't have to write all the terms out every single time we want to do this. We can just apply the formula. Okay, let's see an example of this, of utilizing this. Find a power series for f of x equals 1 over 1 minus x squared. I will point out that this looks a whole lot like 1 over 1 minus x, doesn't it? Which is what I started class with and said we have a formula for this. The big difference is that it's squared. And that creates a huge issue for us because it's not the same, right? I mean, at most you could rewrite that as, don't write this down, okay? You could write this as 1 minus x times 1 minus x again, right? You could do that. But then you would have an infinite power series, right? An infinite series times an infinite series. So it would look like this. Again, don't write this down. This would be x to the n times x to, x to the n again, right? How do you multiply power series? We haven't done that yet, right? We're going to do it, but we haven't done this yet. Because think about it. I mean, this is an infinite polynomial right here, right? It starts out as 1 plus x squared, and it goes forever. And you want to multiply that times 1 plus x squared forever. So how do you multiply out expand polynomials? You start with the first one, right? And you multiply it over there. Well, you got to do that forever, and then you do the x times that forever, and then you do the x squared times that forever, and then you keep doing that until forever. So it becomes a little bit complicated. Understand? So let me show you a different approach that's not going, well, I'll leave all that there. I'll just put a big question mark there. So somehow this is connected to derivatives and antiderivatives of power series, right? Or else I wouldn't have brought it up. So what I want you to realize is this. Notice that 1 over 1 minus x squared is equal to the derivative with respect to x of 1 over 1 minus x. Do you agree with that? So what I'm saying is, look, take 1 over 1 minus x. Take its derivative from Cal 1. What is the derivative of 1 over 1 minus x squared? Or 1 over 1 minus x? Well, that's the same as taking the derivative of 1 minus x to the negative 1, isn't it? I mean, like if you have 1 over 1 minus x, you can bring the 1 minus x up as the whole thing to the negative 1 power, and then take the derivative. So derivative here, you bring the negative 1 out front, right? Then you raise the whole thing to the what? Negative 2, but then you have to say times the derivative of what's inside. What's derivative of what's inside here? Negative 1. This negative 1 and negative 1 become a 1, right? And so you're left with just what? What's 1 minus x to negative 2? It's 1 over 1 minus x squared, isn't it? Are we on the same page or not? I mean, that's kind of the part of this that's a little tricky, is that you have to be so comfortable with derivatives that you recognize that that's the derivative of this, right? Without that recognition, I don't know what to say. You're stuck? I don't know. But you've seen it now, so now you know to expect that sort of thing, all right? Could happen. All right, so let me get back to what we're saying here. I'm saying that the thing I'm trying to find, right, a power series for, is just the derivative of this. Do you know the power series of this? Yes, don't you? So I'm going to continue this line equals, I'm going to go past all this junk right here. You mean to tell me that what you're looking for is the derivative of that power series? What's the power series for 1 over 1 minus x? Sum n equals 0 to infinity of x to the n, right? That is that yellow part. You following this? I want a power series for this. I realize that it's the derivative of that, but that inside here is actually this power series. So I'm actually looking for the derivative of this power series. What's the derivative of this power series? What is the derivative of a power series? Well, you rewrite the sum, you shift the index, n equals 1 to infinity, and then you apply the power rule to whatever's in here. So the n comes out, x to the n minus 1. Which, if we wanted to, we could write out the first few terms of this. This would be, let n be 1, you get what? If I plug in 1 for n, what do you get? 1, x to the 0, right? So just 1. Plug in 2, I get 2x to the first power, plus 3x to the second, plus blah, blah, blah. So the correct answer, the answer we're looking for is this. Which is equivalent to this. So if you can make that connection, this problem becomes somewhat trivial. Do y'all see it? Yes? Now I want to do one more thing just to show you it can be done. I talked about shifting indexes a second ago, didn't I? Just make a quick note of this, that when we're looking at this was the answer we just got, right? There are going to be times, like very soon, where I'm going to be looking at a power series here, and I'm going to want to make my n down here start at 0 instead of 1. So what I do is I ask myself, what do I need to do to make this become a 0? Well, watch. This is what I'll do. I'm going to replace all my n's with n plus 1's. Everywhere I see an n, replace it with an n plus 1. Okay? Rewrite that sum. Replace all your n's with n plus 1's. Okay, so I'll highlight where I replaced them. Right? All the n's I used to have now become n plus 1's. Agreed? Now look at this down here. Just do a little, this is an equation. Just move the n, subtract 1 on both sides, and wouldn't you get n is 0? Right? So this becomes n equals 0 to infinity of n plus 1 x to the n plus 1. This is the equivalent answer, not n to the n plus 1, x to the n, sorry. This is n plus 1, but these ones go away, and so you just have n up there. I'm claiming that that'll give you the same exact series. And you can check it for yourself. Let n be 0, and what would you get? 1, x to the 0, which would be 1. Plug in 1 now, you get 2x to the first, which is what we had. Plug in 2 now, you get 3x squared, so on and so forth. Yes? So this is just an example of how we can shift indexes. All right, that's what I'm showing you there, how you can shift it. And you can shift it anywhere. Like if this had been n equals 3, I could have put, replace n with n plus 3. And then it would have been n plus 3 equals 3, and then that would have subtracted over, you would have started at 0 again. So you can always do that, all right? Okay. What's the next one I want to do? Express the natural log of x plus 5 as a power series. We have not had that, right? I mean, the only thing right now that we really know about is that 1 over 1 minus u, right? Or 1 over 1 minus x. That's the only one we really know the power series of, right, at this point? Somehow that's connected to this. Okay, good, good. So there's several ways we can look at this. The natural log of x plus 5, right, is not the derivative of something, right, that's connected to this, but it's the antiderivative of something. This is equal to the how do I say that? The antiderivative, right, the integral of what with respect to x? 1 over x plus 5. Do you agree? The antiderivative of 1 over x plus 5 is the natural log of x plus 5. Again, how do you know that? Because you took Calc 2, right? Yeah, but you passed that test? No? This is techniques of integration, right? Anytime we had 1 over a linear expression, we always went to natural log. So those become hopefully automatic at some point. Hopefully that point is sooner than later. All right, so that's it, right? Do you know a power series representation of this? Well, let me see. Does it look like this? Not quite yet, right? So I'm going to do some work first. I'm going to kind of stop this problem for a second. I'm going to look at 1 over x plus 5 as first 1 over 5 plus x. Then I'm going to do what we did last class. I'm going to pull a 5 out of the bottom, which will make this a 1 plus 1/5 x, right? You agree that's the same? So here's what I've got. I've got 1/5 times 1 over. Now I need to change that 1 plus 1/5 x into subtraction, right? So it'll become 1 minus negative 1/5 x. We all good with this? So I've changed this into this to try and get it to look like 1 over 1 minus u. Yes? 1 over 1 minus u. And now, using the formula, I know that this turns into 1/5 times the infinite series, right, the power series, n equals 0 to infinity, of u to the n, right? U to the n, which is negative 1/5 x to the n. You all buy that? Understand that? Have any questions? Okay, now let's go back up there, okay? Well, let me see if I'm really ready for this. I'm about to say that everything in that parentheses here, right, is equal to this sum. Yeah? And in order for me to use the integration thing, right, if I want to integrate something, integrate a function, I can just use this formula, right? But the power series that I'm integrating has to look like this. So I have to have my c sub n peeled off away from my x to the n. And my question to you is, do I have my c sub n peeled off my x to the n? Not yet. I can do a little more work here, right? What I can do is this. I can say 1/5 sum n equals 0 to infinity, and then what can I put here? Negative 1/5 to the n, then times x to the n, right? This is the same thing. I'm just peeling these two apart so that hopefully you can see that this right here is my c sub n, and this right here is my x minus a to the n. And when we were doing this before, I said that this was something we wanted to do later, right? Because something, and that's why, because when we do the integration formula or the differentiation formula, you want to separate that constant term out from the power, the x to the power. Pardon? I'll give you one. It'll come in the next section. Yeah, we won't have it here in this section. Is okay? All right, so now let's go back up. Or actually, I'll bring that thing down here. We want this up here to be equal to, continue this down here, right? Whoa. This will be equal to what? Integral of this right here. So it's the 1/5. It's the series n equals 0 to infinity of negative 1/5 to the n x to the n. All of this with respect to x. Now, what do you think about that 1/5 out, the 1/5 out front here? You can pull that out. It's a constant. It's integration. Constants can come out. This 1/5 is independent of what's happening in here. So I can pull the 1/5 out. And now I need to integrate this power series right there. When we integrate a power series, do we shift the index? No. So I'm just going to go summation n equals 0 to infinity. And then I'm taking the antiderivative of x to the n, right? The antiderivative of x to the n is 1 over n plus 1 times, now the c sub n is still there, isn't it? This is a constant, it doesn't change. Well, it changes with n, but it doesn't change in relation to x. So that stays the same. Notice that. It's the negative 1/5 to the n does not become an n plus 1. The only thing that gets the n plus 1 is going to be the x, right? The antiderivative of x to a power, the x gets the exponent added. Understand? That's why it was so important to peel that negative 1/5 off, because if you leave it in there, then the negative 1/5 is getting the n plus 1 on it. Follow? Okay, now just looking back at this stuff I did a long time ago. How about we write out a few of the terms, all right? Let's just write out a few of these just to get an idea. Our new power series, though, check this out. This is our new C sub n, right? And then this is our new, kind of like our x minus a to the n, so to speak. It's not exactly to the n, right? Because it's n plus 1. But what I'm trying to get you to see is that we have a new power series. We started with the power series. We integrated it. We have a new power series. I want to erase that because I don't want you to confuse that with the C sub n up there and stuff. Okay, just write out the first few terms here. So let n be 0. What'd you get if you plug in n is 0? 1/5 x, right? Now let n be 1. So this is going to become, let's see, we have 1/5, we have 1/2 here. We get negative 1/5, right? So what's 1/5 times negative 1/5 times 1/2? Negative 1/50th x squared. Negative 1/50th x squared. Then if you do the next one, it should be, I'll just write down what it is. We won't go through it. 1 over 375 x cubed. And then it's an alternating series. It just keeps going. With me? Are you turning in the test today? We've already collected it over there. Anyone else who came in wants to turn in the test? Go ahead. Okay, let me see something. What was our series there? It was natural log, right? Of 1 plus 5x? Was that what it was? Oh, no. 5 plus x, right? X plus 5? Okay, I'm going to go to Wolfram Alpha. I'm just going to type that in. I'm going to hit enter. By the way, in Wolfram Alpha, if you use log, log is the natural log. Don't worry. It's see, look, assuming log is natural log. All right, because it actually turns out that, well, go look it up. There's a history on it. It's a little confusing, but okay. So if I go through there, look at this. right there. You see that? Wolfram alpha actually gives me the series expansion of it. So I have, didn't we have 1/5 x, so 1/5 x, then we have minus 1/50th x squared, and then plus x, right? We have a constant in there, natural log 5, it's constant. We integrated, right? Okay, so what I'm getting at here is that Wolfram alpha does that for you. It's amazing that all you do is type in log x plus 5. So you know how in the past you type stuff in, you look down at some of this, you're like, what the hell is all this stuff, right? This is the series expansion. That's your series. Okay, next one. Let's take a look at expressing this is a power series. X plus 2 over 2x plus 1 times x minus 1. Now I'm going to work through this one kind of quick. All right, let's see how you do with this. First of all, that does not look exactly like this, right? On the bottom, you could do each of these, right? This one you could write as this. You could work it out, and then this x minus 1, you could work that out to turn out to be like this. But the problem is that there's 2 of them down here being multiplied, and not to mention we have an x plus 2 up top, right? Partial fractions. Good. You've seen this before. No, you haven't seen this problem before, right? But your partial fractions was your instinct there. Can't teach instinct, right? Can't teach instinct. That's, I don't know why you thought partial fractions, but that's the way it should be. Okay, partial fractions is a good thought here. Now, I'm not going to go through it, all right? I'm not going to show you how to do the partial fractions because we've done it so many times. But if you did it, you would get this, right? So assuming from here to here, you do partial fractions. And now, each one of those, now, so you have separation with subtraction now. So you can do these separately and not worry about it. So I'm going to rewrite this first one. Do you agree that this first one can be rewritten as, let's see, pull out a -1 from the bottom, and I'll put it on top. So it really just flips like this. Factoring a -1 out of the bottom and then putting the negative on top instead gives you that. And then on the other one, without going through all the work, although there's not a whole lot to work to do, I rewrite the 2x plus 1 as 1 minus -2x. We good? And then each one of those you can do with your power series, right? What the heck? I may have broke this. There. So what does that first one turn out to be? What is this? Sum n equals 0 to infinity, right? What about that negative on top there? Pull it out. How about putting a negative in front of the whole series? Right, that -1 comes out. And then what is this series right here? X to the n. Good. And then over here on the other one, minus series n equals 0 to infinity of -2x to the n. Now, we haven't talked about this, and we didn't talk about it in the last one either, but you could come up with the intervals of convergence here, because, right, this says the absolute value of x has to be less than 1. I'll just jot it down over here. The absolute value of x has to be less than 1, and what does the other series need for it to converge? The absolute value of -2x to be less than 1, which means that the absolute value of x has to be less than 1/2, right? That's what that one gives you. So in order for the whole thing to converge, you have to go with the smallest interval you have, which would be what, -1/2 to 1/2? For both of these to converge, you would have to be inside -1/2, 1/2. Because if you go outside of that, one of them converges, but the other doesn't. Does that make sense? So your interval of convergence would be based on that one. But I don't want to waste time with that. You understand you could look at that for each of these. Okay, so now my goal is to get this into a single series, not to subtract it. So I'm going to do the following. Let me just pull a negative out of both. And let me rewrite this sum n equals 0 to infinity x to the n plus sum n equals 0 to infinity of negative 2 to the n x to the n. That all right? Okay. Do both of these series start at the same place? N equals 0? Yes? Okay, if they both start at n equals 0 and they both have x to the n in them, don't they? I'm going to add these two series together now. In other words, I'm going to put them into one statement. This will be sum n equals 0 to infinity of x to the n plus negative 2 to the n x to the n. So I'm really just putting what's inside each of the series together with the addition, right? Adding the insides of these together. And since they both have x to the n, right, I can factor out an x to the n. If I factor out an x to the n from both of these, I will be left with, let's see, what? 1 plus negative 2 to the n, and then x to the n, like that. And I really don't like that negative out here. Can I put the negative in here? Can I put that negative back in? Yes, if I put the negative in, it's a negative 1, isn't it? That negative out here is a negative 1. And what I could do is distribute it into this. It would just distribute through this parentheses. So that would turn that into a what? Negative 1. And then drum roll, please. What would that be? Could we do anything there? Can you do negative 1 times negative 2 to the n? Can you put those together or not? You would have to have that negative 1 also being raised to the n, wouldn't you? Or you would have that negative 1 would have to also be a negative 2. Yes? It's not a negative 2. Right? You following me or not? So the most I can maybe do is make this a negative 1 and then make this a minus negative 2 to the n. And that is my power series. Notice again, I have like a c sub n here, right? And then I have my x minus a to the n. C sub n, x minus a to the n. Questions? Okay, last one, and we'll be done with this section. Same instructions. Express this as a power series. F of x equals x squared plus x over 1 minus x cubed. So I think what I'll do is I'll work a little bit quick through this, all right? Because you've kind of seen a little bit of this, but I want you to notice something. I want you to notice that if I look at just the denominator, right? If the original problem would have just been this, we did something very similar to that a little while ago, didn't we? 1 over 1 minus x, but we had 1 over 1 minus x squared. Yes? Guess what? That is the derivative of 1 over 1 minus x squared. It is. You could check it yourself. Take the derivative of 1 over 1 minus x squared, and you will get 1 over 1 minus x cubed. All right? I'm going to need that, and I'm going to need the problem we did earlier to be able to finish this problem. So now what I'd like for you to see is that this function can be broken up into two terms. This is not partial fraction decomposition. This is simply rewriting this using properties of fractions, right? If you have two terms in a numerator over a denominator, I can break it up into two separate fractions, just like this, can't I? And then what I can do is I can say this is x squared times 1 over 1 minus x cubed plus x times 1 over 1 minus x cubed. What I'm doing is I'm just pulling the x squared out in front and the x out in front because I'm preparing for replacement of this 1 over 1 minus x cubed with a series. So I want to get the x squared out in front of it first. So we said that this 1 over 1 minus x cubed is the derivative of this, right? Can we please go get the derivative of this right now? And then I'll continue from this line over here. I should have said this is going to be equal to something. What was the power series representation? So don't take the derivative yet. Go back in your notes. What was the power series that we came up with for 1 over 1 minus x quantity squared? It was sum n equals 1, 2, whatever, right? Blah, 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 blah. But then I said, remember we could shift the index? And when we, well, not the shifting, don't confuse it, not the shifting of the index when we took the derivative, but remember we got to an answer and it started at n equals 1? And I said if we wanted to, we could get it back to n equals 0? Yes? Let's use that one. Okay? It was the one that was n equals 0 to infinity of n plus 1 x to the n. So you have to go back to your notes. Let's see. Boom, 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 boom. There it is. That was it, right? We got to an answer. This was the derivative, right? We said that 1 over 1 minus x squared turned out to be this, right? This right here. And we said that was equal to this. And then on the next note, I said, well, wait a minute. If I wanted to, I could have moved that index over to become a 0, and it would have turned out to be this. And they were the same thing, okay? That's the one I want to take the derivative of. So here it is. This 1 over 1 minus x cubed is the derivative of this, which is just this. And now do your derivative. What's the derivative of a power series? Well, the index gets shifted, right? N equals 1. And then it would be what? What's the derivative of n plus 1 x to the n plus 1? So what? N comes out, right? And then the n plus 1 is still there. And then x to the n minus 1. So it'll be n, the n plus 1 is still there, x to the n minus 1. Remember, the n plus 1 is our c sub n. The x to the n is our x minus a to the n. So when you apply the derivative to this, the c sub n, you do not touch it, right? You do not touch that when you take the derivative. It stays. It is a constant. The only thing that is affected is the x to the power. That power comes out, and the n plus 1 is still there, untouched. Then you subtract 1 from the power. Questions? We're good? So this and this, both of these, right? Both of these guys right here can be replaced with this power series. So let's do it. So here's where I am now. equals x squared times summation n equals 1 to infinity n plus 1 x to the n minus 1 plus x times summation n equals 1 to infinity n times n plus 1 x to the n minus 1. Questions? Our ultimate goal here is to get a single power series. And right now we have 2, and not only that, we have x's out in front of these, right? So look, remember, this is a power series, right? This, if I were to expand this out, it would be like, I'm just making it up, it would be like something like 2 plus 3x squared, something blah, 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 right? If I multiply that by x squared, doesn't it just bring the power on each of those up by 2? On the x's, just brings them up by 2 for each one? That is the same as taking that x squared, putting it back into the series, and adding 2 to this exponent, right? Is that the same process? And then doing the x out here times this series has the effect of adding 1 to the power here. So that's what I'm going to do next. I'm going to bring those x's back into the series. So this becomes sum n equals 1 to infinity n n plus 1. I'll just write it out. It was x to the n minus 1, and what am I going to put here? Plus 2, right? So just keeping in mind that that plus 2 is coming from the fact that that is going inside there, right? It's going in, so it's adding 2 to the exponent there. So there it is. I'll clean that up on the next line. Plus this one, n equals 1 to infinity of n plus 1, and then x to the n minus 1, but then plus 1. Same story there, which is equal to sum n equals 1 to infinity n plus 1 x to the what? N plus 1. Then over here plus sum n equals 1 to infinity of n times n plus 1 x to the n. Okay. Now, hold on a second. Damn it. We have a little bit of a thing I missed in my notes. Hold on. It's a little bit of an issue. It's actually kind of big. The derivative of this, hold on. What is the derivative of this? Let's just check it real quick. I'm missing a 1/2. If we take 1 minus x to the negative 2 and take its derivative, what do we get? Negative 2, 1 minus x to the negative 3 times negative 1, which is going to be 2 over 1 minus x to the third. Right? 2. I said that the derivative of this is exactly this. It's not. It should be what up here instead? 2, right? Okay, so I have to fix this or else it's going to be wrong. So I'm going to make a pretty quick fix on it, all right? Just see if you buy this or not. I'm going to replace this with 2. Everyone put 2. Do you agree now that's correct? Okay. So when I split this up over here and I do this part right here, I need these to be 2's, don't I? For this to work? Yes? Okay. If I do that, I'm going to go ahead and make them 2's, but that would have needed to have changed the original problem to be 2x squared plus 2x, 2x squared plus 2x. So change this to 2x squared plus 2x, 2x squared plus 2x, and then you pull out and then 2's match. I apologize. I don't know how I didn't see that. I even have my own damn notes written down here. I try not to follow them too much. I mean, are there any questions on that? Because I mean, that's obviously kind of late that I noticed that. This derivative I said was that with a 1, it was wrong. It should have been 2. So to fix it, I could have gone through this whole thing and tried to like manipulate, made this a 1/2 in here. But the easiest fix, just make all those 2's and then it matches up exactly. Is that all right? Okay, now back here. Apologize. If I'm going to put these two together, then what I'm really hoping to have is the same power on x. Because remember, I want to be able to factor the x out, right? I want to be able to factor the x to the n out. The problem I have is that this one is to the n plus 1, the first one, and the second one's to the n. So how could I make this an n, just an n, not an n plus 1? Do what? I could do x to the n times x to the 1, correct? I could do that, but I'm going to do it in a way that seems a little unorthodox. I'm actually going to change my index. Okay? What I'm going to do is I'm going to replace my n with n minus 1. And just bear with me, okay? Follow me through here. See what happens. I want these two to match. I want them both to be n's. So I'm going on my first series only. I'm going to let my n become an n minus 1. And here's what happens. I rewrite the sum. N equals 0. No, not 0. Be careful. 2 to infinity. So if you replace this n right here with n minus 1 and add 1 to both sides, it becomes 2 now. And then what does this become? This n right here becomes n minus 1. And then this n plus 1 becomes n. And then the x to the n plus 1 becomes x to the n. Now my other series, I'm not going to touch, right? I'm not going to touch that one. Now they both have x to the n. Do you agree? But what problem have I created? One starts at 2, the other one starts at 1, right? I want them both to start at 1 or both to start at 2, right? So watch this again. It's not magic, it's just clever, okay? Take this, copy that, new page. Okay, so here's what I'm going to do. If I try and take this back to 1, I'm going to wind up right back where I was, right? So instead what I'm going to do is make this one a 2. Now watch how I do it, because I'm not going to replace n with anything. I'm just going to rewrite this. Do you agree that that piece right there, I should do it this way, that this right here is the same as plus, what would you get if n is 1? Replace n with 1, what would you get? 2x to the first power. So this is 2x, right? Plus, now I would let n be 2, and then 3, and then 4, and 5, right? So couldn't I write all the rest of them like this? What have I done, really? I've just peeled the first one off, right? That's all I did, is I peeled the first one out of that series off so that the rest of it would start at 2 and on. Yes? So what if this had been a 3? Then I would peel the first 2 off. If it would have been a 10, I would peel off the first 9. Okay? Now, the series here in the front I haven't changed. Manipulation of power series. I mean, that's what this is all about right here. We are manipulating these power series to get them all to turn out to be something nice, hopefully. So we have the same sums starting and ending at the same place. We have x to the n in both. Since we have that, we can combine them into the same series. So I'll have sum. Let me put the 2x first. 2x plus sum n equals 2 to infinity of, put those two together, put this, right, added to this over here, and factor out an x to the n. And what would you have? You would have that n minus 1 n plus n times n minus 1, and then x to the n. So all that really is are like the coefficients, right? The coefficients of x to the n, these two coefficients, put together with addition, and then the x to the n pulled out. Can you combine these together? What is this? This is n squared minus n, right? And this is n squared plus n. 2n squared is what that is. So we are there. Equals 2x plus sum n equals 2 to infinity of 2n squared x to the n. I want to show you because there's still something little you can do here, I think. Watch. This is 2x plus, let n be 2, what do you get? 8x squared. And then let n be 3. Right? 18x cubed, right? So I guess what I'm getting at is this one out here, does it really need to be here or not? Just check this out. If we let n be 1, if we did, it's not 1, but if n was 1, what would we get? 2x. Just coincidentally, right? I mean, it actually turns out that this first one would actually come out of this series if I let n be 1. So instead of writing it like this, I could have just written it sum n equals 1 to infinity of 2n squared x to the n, just because that first one happens to also match this formula just by chance. So that would probably be the cleanest answer you could give as a power series right there. If this one, if this would not have worked at 1, you couldn't have done that. Wait, what? Mm-hmm. I'm still not following you. You're saying, what if we had the 2x out there, but then also something else with it? Oh, yes. If they happen to match, then yes, you could. Yep. Okay. That's it. That's it for these power series representations. I thought I had a homework assignment here somewhere. Where is it? I didn't give you all power an assignment off this last time, right? Okay. Okay, so this is off of page 474, 3 through 11 odds. 15, 17, 19. Yeah. Yeah, should be good. All right. What do we got? A 40-minute, 30 minutes? Y'all good? Y'all can be plenty tired next week, okay? After you've had Thanksgiving, give me 30 more good minutes of your attention. I see people falling asleep, and I'm not okay with it. Have y'all ever seen Good Will Hunting? You know that scene where the main character is, I forget his name, but he's talking to the professor, and the professor's looking at some of his work, and he winds up like lighting it on fire, and the professor's all like freaking out. You know what scene I'm talking about? Okay, well, where the professor is sitting there, and he's looking through his work, and in this scene you'll hear it if you go back and watch it. He says something like, oh, "I can see you use Maclaurin here," and he's referring to Maclaurin series there. So most likely, I couldn't see the work, but most likely because it's used so much. When you say you use Maclaurin here, this is usually the reference that's being made. So we're going to be talking about a very important type of series, Taylor and Maclaurin series. We're going to find that they're pretty much one and the same. Maclaurin series is basically a power series about zero. Did I just say Taylor? No. Maclaurin series is a power series about zero, so letting that A be zero. And a Taylor series is a power series where you let X just be, you let A be something, A, anything, zero or anything else. So Taylor series is a very general form. Maclaurin series is a specific form, all right? But what is it, right? So here we go. Suppose that you have a function f of x is equal to sum n equals 0 to infinity c sub n x minus a to the n. And you have that x minus a is less than r, where r is your radius of convergence. So capital R means radius of convergence. So what we have is a convergent power series. We already know this, okay? We know that in this case, f of x can be written as c sub 0 plus c1 x minus a to the first. You've already written this out. You don't need to necessarily write this all out again. Okay, c sub 3 x minus a to the third. I'll do one more, c sub 4 x minus a to the fourth. Plus dot, dot, dot forever. Okay, we've seen that you can rewrite that function as its power series by just letting n take on 0, 1, 2, 3, 4, keep on going. The question becomes, if you know the function, right? Like in the past we knew, I gave you a function, I said find its power series. Like I gave you natural log of x plus 5. And I said find its power series, and we were able to do it, right? But maybe there's an easier way to come up with these constants in front. Maybe there's an easier way, and that's what Taylor mathematician, Maclaurin mathematician, that's what they were looking at. Is there a way, and this is all came from Newton's form of calculus, is there a way to actually come up with these numbers? So let's go after it. Let's try and determine what they are, all right? Do you understand what's being asked? Like, is there an easy way to come up with these constants? Okay, here's what we're going to do. First, we're going to do this. We're going to let x be equal to a. If x is a, then what do you get? You get f of a, right? Look at this equation right here. You get f of a equals, everything is 0 except what? C sub 0. Wait a minute. Was it? This is, no, you don't know what this is, right? That's what we're asking. We're saying, what are these constants? If I give you an arbitrary function, right? I say write out its power series, right? I give you an arbitrary function. I say write out its power series. Is there a way to come up with these numbers? So I'm just going to ask you right now, if I let x be a, what does your function say? What does it say? Your function at a is what? Everything's gone except that first constant, right? But that's telling you exactly what that constant has to be, isn't it? That constant needs to be the function evaluated at a, right? So I know what c sub 0 is right now. I'm going to box it. I know what c sub 0 should be. It should be the function I'm trying to find the power series of, evaluated at the point A. Now, this is where the clever thing happens. Take the derivative of f. So what's the derivative of f? Well, the derivative of c sub 0 is what? 0. Okay, derivative of this right here? C sub 1 x minus a to the 0 power, right? So it's just c sub 1. Then it'll be what? Plus 2c sub 2 x minus a plus 3c sub 3 x minus a squared plus, keep going. Now let me put one more. 4c sub 4 x minus a to the third plus, keep going. Y'all see? We did the derivative just like previously, didn't we? We're just taking these powers, bringing them out, bringing them out, bringing them out, right? This is this. Now let me ask you this. What's f prime of a? Well, if I plug a in here for x, what do I get? 0, 0, 0. So the only thing left is what? C sub 1. I just gave you a formula for c sub 1. It's the derivative of the function at a. What was c sub 0? The function at a. What's c sub 1? The derivative of the function at a. What do you think I'm going to do now? Take the derivative again. What's going to keep happening every time I take a derivative? You're going to get the next piece, right? So look, what would the second derivative, so I'm going to write this way, second derivative of x give you? That would be derivative c sub 1 is gone, but now be careful here. What would this be? Derivative of this. 2c sub 2 plus, what would this next one be? 2 times 3c sub 3 x minus a to the first power plus 4 times 3, or I'll do it this way, 3 times 4 c sub 4 x minus a what? Squared plus dot dot dot. Okay, so derivative c sub 1 is 0. Derivative of this is just 2c sub 2. Derivative of this, the power comes out. That's 2 times 3 c sub 3 x minus a to the first power, and then so on and so forth. Now I'm going to say, what happens if I let x be a again? What do you get? 2c2, right? Which means that 1/2 f double prime of a is c2. We're starting to create a pattern, and this pattern is going to give us a formula. Let's do one more derivative, and maybe you'll see the pattern. What's the third derivative give us? What's f? How do we say third derivative without the prime marks? We do a 3 in parentheses, like this. Do y'all remember ever seeing that? Instead of writing f, like f, if you write f with a 3 versus f with 3 in parentheses, the f with the 3 without parentheses means f cubed. But f with the 3 raised to the 3 in parentheses means the third derivative. So this means the third derivative of f, which means the derivative of that, which is what? Let's see. So take the derivative here. This is a constant. It's gone. Derivative of this would be what? 2 times 3. I agree that's 6, but, right? There's a pattern being created here. 2 times 3, C3, right? What would this one become? Look, check this out. This is where the patterns, you're going to hopefully see it here. What would this one be? 2 times 3 times 4, C4, x minus a to the first power, and then keep going, right? Now plug a into the third derivative. The third derivative at a would be what? 2 times 3, C3. And then divide both sides by 2 times 3. So what you're getting here is that C sub 3 is the third derivative evaluated at a over 2 times 3. And what would the next one be? If we're following this pattern, the next one should be, right, to get C4, it should be, what, the fourth derivative evaluated at a divided by 2 times 3 times 4. But 2 times 3 times 4 is what? 4 factorial, right? And this right here is 3 factorial, right? I'm not putting the 1, but isn't it 3 factorial? And then back here at the second derivative, 1 over 2, that's 2 factorial, right? And the first derivative was what? This is like a first derivative at a over 1, right? So 1 factorial. And then check this one out. What derivative is this? If I don't take the derivative, what derivative is it? We actually call it the 0th derivative. And so this is the 0th derivative divided by what? 0 factorial. 0 factorial is 1, right? There's a pattern in this. And that's what the Taylor series is. It's a way of giving us a formula for generating the series. I hope you like that. That's good stuff right there. So here's what we get. We get a general formula. The formula is this. Our C sub n should be equal to the nth derivative evaluated at a over n factorial. And that is defined for all n. Now, we have to have some things happening for this to work. We have to be able to take derivatives, right? The function that we're trying to find the power series of, we must be able to take its derivative. And not only its derivative, multiple derivatives, right? If we can't take the derivative of it, we're not going to be able to come up with a power series representation for it. We will struggle, right? And we've seen in Calculus 1 that sometimes it's easy to take derivatives and it gets nicer and nicer, and then sometimes you take derivatives and it gets worse and worse and worse, right? Depending. So we'll just have to see, okay? So here's our big theorem. I'm actually going to put it on its own page. The theorem says this. This is the theorem. This is the definition of basically a Taylor series of a function f at a. You will also hear or see books sometimes say this is the Taylor series of f centered at a, or the Taylor series of f about a. Here's what it is. If f has a power series expansion, in other words, if we can write it as the sum c sub n x minus a to the n, well, I'll write it out. In other words, f of x can be written as sum n equals 0 to infinity c sub n x minus a to the n, right? If your function does have a power series expansion, if it does, then the c sub n's are equal to the nth derivative at a divided by n factorial, which in turn means that your function can be written as this power series. N equals 0 to infinity, f prime, not f prime, f, the nth derivative at a over n factorial, x minus a to the n. Yes, that is the big daddy right there. Of course, we always have to assume here that we are within the radius of convergence, all right? If we're not within the radius of convergence, this isn't going to work. Now, if a equals 0, how does this formula change? If a is 0, the formula becomes this. Everywhere you see an a, put a 0. The one on the bottom is called the Maclaurin series. The one above it is your Taylor series. So do you see what I was saying? The Taylor series is more general because you can let A be anything you want. The Taylor series is a specific series, Taylor series, when A is actually equal to 0. Understand? That's a specific series. Can you leave, please? Just leave. Please. Thank you. All right. Okay. So I would like to show you an example of this formula being used. You have books bag or anything in there? No? Okay. I just don't like looking at people sleep. All right, so here's an example. I want you to find the Taylor series of this function. And the first thing that you should come to your mind is, wait a minute, hold on. A Taylor series is an infinite series, right? Of powers of x that somehow represent your function. And if you look at that, you're like, well, wait a minute, that already is powers of x, isn't it? Isn't it? I mean, it's an infinite series. It starts out x, go backwards because it go the opposite direction. So it's 1, then x squared, then what? Nothing, right? 0, 0, 0, 0, 0, isn't it? That is an infinite series, just a bunch of them are 0. I claim that we can get that using this formula. Now, you would never need to get a power series on that because you have it, but I want you to see that the formula will generate this function. So our series should be equal to, this f of x should be equal to the sum n equals 0 to infinity, the nth derivative at, well, let's see. Does it look like we have x minus a in here anywhere? I mean, a here looks like it's what? 0? So let's do the nth derivative at 0 over n factorial x to the n. Let's see if that Taylor series, I could also call that a what? Maclaurin series. Let's see if that Maclaurin series is the same as that function up there. So what I need first is I need some derivatives, right? So what is the 0th derivative of the function? It's just x squared plus x plus 1, right? What is the first derivative of the function? 2x plus 1. What is the second derivative of the function? 2. What is the third derivative of the function? 0. And from there on out, it's 0, isn't it? So I get all my derivatives here. Now what I'd like to do is write out this sum. This sum is equal to, see if you can follow me here. First start with n is 0. What is the 0th derivative of the function evaluated at 0? So go to the 0th derivative, plug 0 in for x, and what would you get? 1. So I have 1 times, or sorry, 1 over. I forgot to put 1 over, and then what? I'm plugging in 0, 0 factorial. I'm going to put 0 factorial so you know where I'm coming from here. Times x to what power? The 0, right? Plugging in 0 to start here. So does everyone see that that is the first term of this power series? Yes? Now go to the next one. Plus, so now what I'm doing is I'm plugging in 1. What is the first derivative of the function evaluated at 0? So plug 0 in here, and what do you get? 1. 1 over, what? 1 factorial, x to the first power. With me? Plus, now, plug in n is 2. What is the second derivative evaluated at 0? Well, the second derivative at 0 doesn't matter because it's just always 2. So this is 2 over what? 2 factorial, x to the second power. Now let let n be 3. The third derivative doesn't matter. Third derivative forever, the rest of the way is 0, isn't it? So everything else is 0. 0 plus 0 forever. What is this first term? 1. Plus, what's this? X plus, what's this? X squared. That's the original function, right? It seems dumb to take a polynomial and write it as its power series because it should actually be itself. But that just goes to show you that the formula will generate it. Some amazing way it does. All right? I have time for one more. This one will be more significant. I would like this power series for sine x. What's the power series for sine x? Okay. You know what? Can we do cosine x? I'll do sine x next class. Cosine x. All right, so if I'm going to write this using the formula, I'm going to need derivatives, right? And again, this will be a Maclaurin series because it appears that my x is just x minus nothing, right? This isn't like cosine of x minus 3 or something like that. So I'm just going to assume it's Maclaurin series. And so that is a Maclaurin series right there. So now I need to get some idea of what's going on with the derivatives. I'll do that on the side. What's the 0th derivative of the function? Just cosine x, right? What's the first derivative of the function? Negative sine x, right? What's the second derivative of the function? Negative cosine x. What's the third derivative of the function? Sine x. What's the fourth derivative of the function? Cosine x. And now what's going to happen? It's going to keep repeating itself, right? Now, next to this, and I didn't leave myself a lot of room, aren't we going to do that 0th derivative and we're going to plug in 0? Aren't we going to do that over here when we start letting n be 0, then 1, then 2, then 3, then 4, right? So what would happen if I plug 0 into this? What would I get? What's cosine of 0? One. What's the first derivative at 0? So what's sine of 0? 0. Okay. What's the second derivative at 0? Well, cosine of 0 is 1, but then it's negative, right? So you get negative 1. And then you're going to get 0 on the third derivative. And then on the fourth derivative, we start the pattern over, don't we? We get 1. And then this will keep repeating itself, right? So it goes 1, 0, negative 1, 0, 1, right? 0, negative 1, 0, 1, negative 1, 0, right? It just keeps going like that. All right? Questions? Okay, let's try and write this power series out. I'm going to do it down here on the bottom. This should be equal to, if n is 0, we get what? 1 over 0 factorial, right? X to the 0. Okay, plus, then what? The first derivative, right, at 0, which is what? 0 over, now it's going to go to 0, right? But I'm going to put 0 over 1 factorial x to the first. Then we go to the next one, which will be plus, what's the third derivative? Negative 1 over 2 factorial x to the second. Plus, what's going to happen here? 0 over 3 factorial x to the third. Plus, now the cycle repeats itself, right? As far as those numbers on, so 1 over 4 factorial x to the fourth, plus 0 over 5 factorial x to the fifth. Then what? Plus negative 1 over 6 factorial x to the sixth, plus, and I'll stop there, right? It just keeps going. Bunch of these are gone, right? A bunch of these are zeros. That's 0. That's a 0. That's a 0. And now what I'd like to do is see if we can rewrite this in a cleaner manner. This is just what? 1, that first term is 1, minus 1/2 x squared, plus, what's 4 factorial? 24 x to the fourth, and then what? Minus, what's 6 factorial? I don't know. What is it? 240 something. I don't know. 6 times 5 times 4 times 3. I'm just going to put 6 factorial. Okay. Look, doesn't matter. All right. Y'all okay with this? Seem all right? I would like this written as a sum. So tell me about this here. What's happening to our series? It is alternating, right? It is starting with the positive. How can I make that happen? Negative 1 to the, and I'm going to start at n is 0. So we'll just make it negative 1 to the n. And then what's happening on the bottoms? I've got 0 factorial, then 2 factorial, then 4 factorial, then 6 factorial. Those are all even numbers, right? Starting with 0. So I need to do what on the bottom here? To make evens, 2n factorial, but hold on, because we're starting at 0. So will that do it? That'll be 0 factorial will be my first one, and then when I let n be 1, it'll be 2, and then 3. Then I'll get 4, right? So 2n factorial. Is that all right with everyone? Alternating, even number factorials. Starting with 0 factorial, plug in 1, you get 2 factorial, plug in 2, you get 4, plug in 3, you get 6, right? So there's your factorial, and then the rest of it's what? X to the, those are all even numbers, right? Starting with 0 to n. This is your power series for cosine x. We're going to end right on this beautiful note here. Do y'all remember when someone told you one time that cosine was an even function? Do you know why now they call it an even function? Because its power series are all even powers of x, right? They're all even powers of x. Also, do you remember the property even meant this, right? Cosine of negative x meant that you had cosine of x. That if you had a negative inside cosine, it would be the same as just replacing it with a positive. Why? Because every power up there is even. So if you plug a negative number in, it's not going to make a difference. It's going to get either squared, or to the 4th power, or to the 6th power, or to the 8th power. So it doesn't matter. You may as well have plugged x in, right? The power series shows more why it's even than anything else. Guess what's going to happen when we do sine? They're all going to be odds. It doesn't make sense. Why? These derivatives are going to be shifted a little bit, right? These derivatives here, it's going to start out sine, then cosine. So, we're going to have 0, then 1. So it's going to shift everything over. So now all your evens will be dead, and you'll have odds. And when you have odd numbers, and you take odd powers, if you have odd powers, and you take a negative number and you raise it to an odd, the negative will stay, right? So what happens is you get this property of sine that says sine of negative x is equal to negative sine x. So it changes everything by sign, and they call sine an odd function because all the powers are odd. Okay. You know what? When you take any function, you call it even and odd. I bet that if you find its power series, it'll be all evens or all odds, right? It would make sense that way. Not every function, though, is even or odd. You can be even, odd, or neither. So the ones that have evens and odds in them would be the other stuff. Yeah, good question. Well, how would you... Yeah, well, cosecant and secant are reciprocals, so they should follow the same thing. But to show it, what you could do is you could actually just put cosecant here, and then you could find the list of derivatives. That would be nasty, though. It might be better to do a different way. Okay, I am out of time. We still have a lot to do in this section, but I'm happy that we're here. I think that we're probably going to finish this section up next class on, Tuesday, and we'll start chapter 9. I want you to see parametric equations. I'll introduce you to the polar coordinate system. And that's all stuff that you'll see later if you take more math, but it's something you can pick up quickly. So if we don't get too deep into it, we don't. My ultimate goal is next class to show you this is true. To show you that e to the I pi minus 1 equals 0, plus 1 equals 0. I'd like to show that to you next class. Has anyone ever seen that formula before? It's considered to be the most beautiful equation in math by some people. I mean, your definition of beauty is relative, right? But most beautiful equation. Did I say function? Yeah, this one, because look, I know y'all can go, but it has all the most important numbers in mathematics in it. Has the multiplicative identity, which is 1. It has the additive identity, which is 0. It has pi, which is always circumference over diameter. It has e, which is the natural exponential base. We love that. And it's got I, which is the imaginary unit. And it turns out that this equation right here is true, which really means that all I'd have to show you is that this is negative 1, right? So I'll show that to you next class. We'll use power series to do it. Have a good day. Okay, sure. Let me shut.